All right. So first, reiteration of a previous warning. You guys need to be more careful. So with homework two, a lot of you guys did this thing where like you would try to show two sets are equal by like starting with like set definition, and then just doing like logical manipulations inside of the set builder to like do dot 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 dot. Okay, these sets are equal, but uh I don't know if you noticed, but a lot of the times when you try to do that, it ends up being very clunky. It ends up being just a list of like manipulations. It's not very clear what happened. You're kind of just doing almost. It kind of just feels like you're doing algebra. Instead, what you should have done is done universal instantiation, like we did in class for lecture two, and show that this guy's a subset of this and that guy's a subset of this, and then they're equal. Also, a nice thing you can do, which if you looked at solutions, you would have seen, is that a lot of times these proofs are reversible. So what I mean by that is when you're showing subset in this direction, it turns out that if you just literally go backwards through your steps, you'll show subset in the other direction. This tends to be the case for some of these simpler proofs. So when that's the case, when you're showing the reverse direction, you can literally just say the proof above is reversible, and that's sufficient. But in general, being careful, sort of you need to grow this sense in the back of your mind that something's off, right? I haven't quite justified this step, so maybe I've gone down the wrong path. Maybe it's hard to prove it this way, or something along those lines, right? And we'll try to build this intuition of something's wrong over time. Okay. Any questions? Suppose I should open the chat. No, all right, let's go ahead. All right, induction. You guys should be very excited for this. It's induction is very powerful and it's very nice. Very, very nice. Okay. So mathematical induction is something along the lines of trying to prove a Boolean function is true across all the natural numbers. And it's not precisely this. It turns out induction can be a lot stronger than this. You can even do induction on real numbers, which is very crazy. But we'll return to that idea later. So actually, let me draw a picture because I think a picture is pretty useful here. The idea of induction is this. Yeah, you imagine like you have some dominoes, but our dominoes will be circles. And I want to do something to all of these, and of course it will continue. So I'll have to do two things. First, I have to knock over this domino, right? Otherwise, we don't start anything. We don't knock over the first domino. And then I need to check that for any arbitrary domino, like maybe this guy, I need to make sure if that this is knocked over, it will also hit the next guy. So what happens as a result is this is known as the induction step. So if I have the induction step and I have the first step, what happens is that as a result, my induction step makes sure that everything gets knocked over. Oh, I suppose it will go like that, and so on. So the point of induction is that we just have to really prove this base case and this inductive step, and we have done it. We've proven the statement is true for everything. Does that vaguely make sense? Okay, I'm gonna assume that's yes. Okay, cool. So it can be a little bit more general. We can say we'll prove the first k by hand, the first k. So here in my picture, I only knocked the first one over, but maybe I have to manually knock over the first three. Maybe there's like some weird stuff going on in the beginning, but after I knock over the first three, then I know that everything else will be knocked over. So the template is like this. The first step is the base case. We'll prove that the statement is true manually for some k at the beginning. And then the second step is the inductive step. And we arbitrarily pick some natural that's at least k, right? So we'll universally instantiate n to be at least k. And we assume that it's true. We assume that f of n is true. And then we'll show that f of n plus 1 must follow. So we showed that f of n implies f of n plus 1 as long as n is big enough. So that's the same thing here. We showed that for, for any domino out here, it must knock over the next one. Okay, and now you know what induction is, and you know basically all the standard proof techniques. Basically every proof technique looks like something you've already seen so far. So we'll build on induction more, but it turns out that basically the other forms of induction are actually just this, but like dressed up a little bit more. Okay. So now let's do a very, very simple example of proving a statement with induction. But this is a statement that is obviously true. So for proof for any natural n, there's a subset S of the natural numbers where the cardinality of S is n. Right. So this is obvious, right? Because we can just pick for any n the first n numbers, the first n natural numbers, and that set will have cardinality n. So this statement is very trivial to prove, right? You just do it directly. But we're going to do it by induction just so you understand. So it turns out that there's nothing weird going on here. So we can just pick k equals 1. So k equals 1 means that we just need to prove f of 1. Okay. So I need to prove f of 1. And f of 1 is clearly true because if I pick s is equal to the set containing 1, then the cardinality is 1, and f of 1 is true. Okay, so this was the base case. So now if I look at my template again, for my inductive step, I need to arbitrarily instantiate n that's at least 1. So let's do that. So n is at least 1. And we assume f of n is true. Okay, so we assume that the nth domino has been knocked over. So as a result, there's some subset of the natural numbers with cardinality n. I can assume I have this S. And now I need to prove f of n plus 1. So somehow using this set, I need to construct another set which has one more natural in it. So S is finite. So that means that S has a maximum. And so if the maximum of S is m, then I just throw m plus 1 inside of there. And I call this new set S prime. So S prime is definitely one element larger because m plus 1 is not in the set. Is not in the set S because it's one larger than the greatest element. So as a result, I've made a subset of the natural numbers that has n plus 1 elements, which means f of n plus 1 is true. So I've given you a way to construct directly a set with n plus 1 elements given a set with n elements. So does that make sense what I did there? Cool. Another way you can kind of prove this using something that you don't have access to yet, but I'll sort of gloss over this detail, is suppose you weren't convinced that doing the base case and doing the inductive step yields that it's true over all the natural numbers. Suppose you weren't convinced of this statement. Then let's say k is the first time where is the smallest number where f of k is false. So if f of k is false, but it's the smallest the smallest value that makes f false, then f of k minus 1 should be true. But then by the inductive step, f of k minus 1 should imply f of k. So it's not possible that there's any k for which f is false. Okay. And this is a very very standard looking induction problem. Prove that for all natural n, this sum identity is true. So probably you guys have seen this before. So we're taking the sum of the first n natural numbers, and we want to show that it's just this. I think it's n choose 2. So you can prove this kind of naturally. You could say like, I can't, not allowed to undo all of that, unfortunately. So normally the way you do it is you say, okay, 1, 2, n minus 1, and so say, okay, this guy is n plus 1. You say, okay, this guy's also n plus 1. And then, okay, it turns out we have like n over 2 of these because, well, yeah. you match the halves. So that's vaguely how you could prove it directly. But it turns out it's just easier to do it with induction, a little bit more rigorously. So we'll do that. So I have a step 0 here. I'm just actually defining what my Boolean function is over the naturals. And it's precisely that we have equality here. So the equality here is interpreted as a Boolean. Okay. Now I pick k equals 1. It's again, it's very very normal to something alive. What was I saying? Yeah, it's very normal to pick k equals 1 to only have to do one base case. It's can only think of a handful of proofs where you have to do actually more than that. But so let's prove f of 1 then. Okay. It turns out it's very simple. So the sum of the first 1 numbers is 1, and that turns out to be equal to 1 times 2 over 2 over here. So f of 1 is true. Very nice. And now it's kind of like doing the inductive step, especially for these kind of identities. It usually just looks like picking up a hammer and hitting the problem really hard until you've beaten it in the right shape. So I usually don't remember how to do these. I just know that if you hit the hammer hard enough, it'll work out. So anyways, so assume n is at least 1 and assume f of n is true. So since f of n is true, we know that this is true. Okay, we have this. And now this is the hammer hitting. So I want to show f of n plus 1, right? So I want to show that if I had an n plus 1 here, it would be equal to replacing n here with n plus 1. So I'm trying to get this in the end. And the thing is that since every time I give you an induction problem, you know it like works out, you kind of know that this over here needs to be equal to this. So all that has to happen in between is just an algebra. So how do we do that? Well, we want to make use of the fact that we know this is true. We know f of n is true. So how do we do that? Well, we want to change this sum to look more like this. The way to do that is just to pull out the n plus 1, right? Because the sum of the first n plus 1 natural numbers is just the sum of the first n natural numbers plus n plus 1. So I've just pulled this out. And now this, I know what this is equal to. I know it's equal to this quotient. And then now I just have some algebra to do, and I'll save you the burden of looking at this. It's just annoying. You know it has to be equal to this. Okay. So for this kind of induction on a formula like this, there's really nothing to do. Just hit the hammer hard enough. Okay. Does it make sense? Okay. Thank you guys for your intermittent yeses. I appreciate it. Okay, now we'll do something a little bit more interesting. I actually really like this one. So first we need to start off with a claim. So we'll talk about GCD. So GCD AB is equal to GCD B minus A comma B. And actually, there's a better way to do this. We could replace this minus sign with a modulo. And then that is actually just the Euclidean algorithm for calculating GCD. And you can do that in log time of these inputs. It's very nice. Okay, so I haven't read this proposition in a year, so I will try to explain it as I'm reading it. Okay, so what do we have here? A number is a divisor of a and b, if and only if it's a divisor of b minus a and b. Okay, so we have what's going on here? Okay, sorry, I'll not distract you with this. Okay, so we have two things over here. The number needs to be divisor of a and b, and two things over here. It needs to be divisor of b minus a and b. Okay, so it's a little bit strange. You have being a divisor of b on both sides, but it turns out that if we prove this claim, it's exactly equal to this. Okay, so let's have g be our number. Let's prove the forward direction that this implies this. So g is a divisor of a and b. So that means that since G is the divisor of A, we have some K such that GK equals A, and we also have some K prime such that GK equals B, GK prime equals B. So now I can just manipulate these two equations, and I have G times the difference of K prime and K is just B minus A. So since G times some integer is B minus A, we have G divides B minus A. And since we assumed G divides B, then we also have that G divides B, obviously. So we have the forward direction. Being a divisor of A and B means you're a divisor of these two. And yeah, the backwards direction is pretty much the same thing. It's just you do GK equals B minus A and GK prime equals B, and you get exactly the backwards direction. So why did I bring you through all this pain? Well, it turns out there's a nice thing you can do induction on. And I'll save this detail for yourself. You can think about why this shows the GCD is actually equal from this. Okay. So most of you guys should know Fibonacci, but I'll just repeat it for anyone who's not familiar. So f of 1, so the first number in the sequence is 0. F2 is 1. And then afterwards, for every n greater or equal to 3, f of n is the sum of the previous two numbers in the sequence. And now we have a really nice statement. For every natural n, fn and fn plus 1 are coprime. And we are going to use this proposition here. Okay. So we want to prove that every two consecutive Fibonacci numbers are coprime. They share no divisors, or equivalently, their GCD is 1. So let's start by induction. So stage 0, we'll say our Boolean function takes in integer n, and it's true when the nth number is coprime with the n plus 1 number. Okay. Now the base case will be simple. We will just pick k equals 1. And to prove f of 1 is very simple. The GCD of 0 and 1 is 1, because the only divisor of 1 is 1. So the GCD must be 1. Okay, so as usual, the base case is usually pretty easy. It's actually really rare for the base case to be hard, so it's nice. And now we'll assume f of n is true. So we'll assume that two consecutive numbers are coprime. Now we want to think about f of n plus 1 and f of n plus 2. And we want to show that those guys are coprime. So we look at GCD, fn plus 1 and fn plus 2. But using this proposition from before, you can actually just rewrite this. And well, okay, so first we will replace f of n plus 2 with this definition. F of n plus 2 is the sum of the two previous Fibonacci numbers, fn and fn plus 1, right? And then now we use the proposition, and we notice that we basically get to subtract out the fn plus 1 from this guy because it's right here. So as a result, it's coprime. So I think it's a really, really neat fact. And there's actually a lot of really interesting facts about Fibonacci sequence that you can prove by induction. And then the proofs are usually pretty simple, which is nice. Okay. This makes sense? Oh. Oh, yeah. So I'm writing out the Boolean function for clarity for you. So don't actually write the proof like this. So yeah, that's a good question. How should I write a proof for this? So I would write it something like this. We will proceed by induction. Let's make this a little smaller. Or actually, I can just make it like this on n. So the first two. No, I don't have soft wrapping. Okay, I guess we'll do this. Two Fibonacci numbers are coprime, as 0 and 1 are coprime. It's really annoying. And then I'll suppose fn and fn plus 1 are coprime. And then I would like show you the actual stuff I did. Okay. Does that make sense? How this proof worked and how to word the proof? Cool. Okay. So it's kind of similar to the previous showing this some identity is true. Because really all we did was we set up the template and it almost proved itself, right? When we start with f of n, right, we start the assumption, and we want to make it look like f of n plus one, or sometimes we start the other way. We start with f of n plus one, and we want to make it look like, oh sorry, yeah, here we actually we start with f of n plus one, and we want to make it look like f of n. You either go one way or the other. Um, and these proofs sometimes they kind of just write themselves, which is really convenient. Okay, so we'll have some fun here. So there's a lot of common proof errors. So I'll go over some of them now, and some of them come from this link here. So feel free to visit it. Okay. So let's have a, b, and c all be integers. So prove that if a divides the product of b and c, then either a divides b or a divides c. Okay. So here's my so-called proof. So suppose we pick integers a equals 5, b equals 3, and c equals 10. So the this is true. A divides bc because 5 divides 30, right? Because 5 times 6 is 30. And it also follows that a divides c, right? Because 5 divides 10. 5 times 2 is 10. So I have proven that I've proven that if you divide the product, then you divide one or the other. So obviously the error here is universal instantiation. So this is kind of like a stupid way to do universal instantiation wrong, right? But it's sometimes people are convinced by this, where I have just picked specific numbers. Hello. Yeah. So what I've done wrong here is I've picked specific numbers. So I've imposed something much stronger than a, b, and c being integers. So definitely never do this. But there's often much finer ways of, or more subtle rather, ways of making this type of error. Okay. Here's a definition now. We have something called a Euclidean domain. Do you need to know what a Euclidean domain is? Not now, but when you take 452, which is algebra 2 in the honor sequence, you will learn about Euclidean domains and all kinds of funny looking rings. But basically, in general, for the Euclidean domain, we have some kind of metric. In this case, we'll just use absolute value for our integers. And for every two elements, a and b, where b is not 0, we can do a so-called division. And this is not always going to look the way you think it does for division. But when we work in the integers, what happens is for these two a and b, there's always a unique q and r, such that a is equal to bq plus r. And r is bounded by the absolute value or whatever metric we put on the space applied to b. Okay, so what does this mean, right? What is this really strange looking thing with all these variables? Well, all it's saying is that if I wanted to divide a by b, my quotient would have been q, and my remainder would have been r. Okay, so let's say a is 10 and b is 3. Then my quotient would be 3, and my remainder would be 1. That's all. Nothing really strange going on here. And we always try to pick these variable names, so it's pretty clear that a over b has a quotient q and a remainder r. Okay, and this is called Euclidean division. And we have I present it as a note, not even like a proposition, where I would go ahead and prove it. But I just tell you the integers are Euclidean domains, so you can always do this. Okay. Yeah, blah blah blah. Okay, explain that. Okay. Okay, now I define modulo. So modulo, okay, I guess maybe somebody's rushing the recording and they don't know modulo yet. So let me explain it properly. Modulo is precisely what you get if you apply Euclidean division to a and b, and you were to get some value r. So because r is unique, remember that when you do Euclidean division, both q and r are unique. So a mod b is unique. So I can always define some remainder r that I would get as long as b is not 0. So a mod b is just the remainder you would get. And we can also extend a little bit what we can talk about with modulo. We can say that two numbers are equal modulo b if hang on, this is a typo. Okay. So I'll correct it later. But a is equal to k modulo b. So also I should maybe make it a little bit more clear. So a is equal to k mod b if what do I have here? Yeah, I should have a mod b is equal to k mod b. So if I were to apply Euclidean division to a and b and to k and b, I should get the same thing if I want them to be equal in the modulo sense with respect to b. So maybe I'll just do a quick example. So let's say a equals 4, k equals 7, and b equals 3. So a equals to k mod b because a mod, well, 4 mod 3 is equal to 1, and 7 mod 3 is equal to 1. Okay, sorry if I bored anybody, but I want to make sure everybody knows what is modulo. Okay. Um, oh, remember there's a restriction on R. R needs to be like this. R needs to be non-negative, and it has to be less than the absolute value of B. So there's no like there's nothing further you need to say. So if you know floor division, then Q will simply be the floor division of A and B. And then R will be uniquely determined because if you know A, B, and Q, then you can solve for R. So maybe let's talk about it a little bit more then. Yeah, let's do that. So let's say A equals 10, B equals 3. Okay, so we have 10. We're trying to split it apart, right? That is what we do with division. So we'll have 3 times Q plus R. So my claim is that um, Q is unique and R is unique, and they're independent of each other almost. Well, not even almost. They are. They are independent of each other. Um, so it is easier to solve for Q first, but I could also solve for R first. But basically, there's only one value for Q that I can actually get R that is at least 0 and less than 3. Right? So let's say I pick Q equals 2 by accident, right? So I get 10 equals 6 plus R. Well, then R will be too big, right? So if R is too big in some sense, I need to make Q larger. So I need to try again. So maybe hang on. Why do I have a 6 here? Oh yeah, because I had times 2. So I need to make Q larger. So now let's try Q equals 3. Well, now this is 9. So now R is 1. But now if I make Q a little bit larger by mistake, then well, now R would have to be negative. So now I've made it too big. So you can kind of see the sketch of the proof that you can that well, specifically that the integers are Euclidean domain. Okay, I hope that makes sense. Yeah, cool. And maybe I'll include the example in the notes for next time. Okay. Now let's use this knowledge of Euclidean division. So what do I have here? Let a and b be integers, where a is 1 mod 3. So if I did a Euclidean division with a and 3, that remainder should be 1. And b is equal to 2 mod 3. So if I did Euclidean division with b and 3, then the remainder would be 2. And now I want to prove that the sum of a and b is equivalent to 0 modulo 3. Okay. So I should also add some parentheses here because I think it's not clear, but basically these equalities are under modulo 3. It is not supposed to be read as 0 mod 3, which would just be 0. This equality is under modulo. And same here. This equality is under modulo. This equality is under modulo. Okay. Now here's my fake proof. Let A and B be arbitrary integers such that A equals 1 mod 3 and B equals 2 mod 3. So far, everything seems okay. I've done universal instantiation, just okay. Now let's do division algorithm on these guys. So there's some q such that A equals 3q plus 1. That seems reasonable. The unique remainder is here, and there has to be some q for this. And we'll do division algorithm again with B equals 2 mod 3. So since B equals 2 mod 3, we have this. There must be some q such that we get a remainder of 2. Now I do some algebra. I'll spare you from reading the algebra, but basically if you do the algebra correctly, you get A plus B is equal to this thing. So as a result, we see that A plus B is divisible by 3. So now remember that division algorithm is unique, right? So I've written A plus B as some number times 3, right? So that means that in here, the remainder is 0. So that means that the remainder is uniquely 0, which means that A plus B mod 3 must be 0, because I showed the remainder here is 0. So as a result, A plus B is equal to 0 under modulo 3. So the error here is very simple. It's just that I have A equals 3q plus 1 and B equals 3q again plus 1, or plus 2. And using this q again is not allowed. And actually, the reason I bring this up is because one day I was sitting in my algebra class, my abstract algebra 1 class, and I was a big idiot. I was very inexperienced. And we were doing like problem solving session. And we're all struggling on a proof. And I'm like, hey guys, I think I figured it out. And I made this mistake. And nobody noticed it. So they were like, oh, okay, cool. And then I don't know how that went unnoticed, but I was very embarrassed when I realized that I used the same variable twice. I think it actually was with a similar circumstance where I had two things divisible by a number and I used k twice or something, and that was stupid. Anyways, yeah, just be careful never to make this mistake. It's very embarrassing. Okay, now my favorite example is it's a little bit non-trivial, and it will use some math you're not familiar with, and there's no reason to introduce it now. It will be too confusing. But the logic is there. The logic being wrong is there. Okay, so we have a Daikon radius number. Okay, I mean integer x. So we write this as dr of x. So this number of some integer x describes the number of graphs of isomorphism class x to the p. Well, this doesn't mean what you think it means. This is not x to the power of p, but it represents a class. And this p is the smallest prime larger than x. Okay, so it is written as dr of x, which I just mentioned. So okay, we have this funny looking number. So basically, you can just think of it as a function from integers to naturals. Okay. Oh, naturals plus 0, because dr of x can be 0. Okay. And now we'll try to prove the following statement. Prove that every set of integers of size n all have the same dr number. So it's a very funky looking claim, right? So I'm saying that any set of integers, they all have the same dr number. It's pretty strange, right? Because then why would we care about dr numbers if they're all the same? But I'll still prove it. I'll prove it by induction, which we just learned. Okay. So first, let's describe my statement. So f of n is defined by the following statement. I should have written this in English instead of using logic, but whatever. So for every subset of the integers, if S is of size n, this implies that for every two elements in S, they have the same dr number. So this is a very typical way to show that for everything in the set has the same property. You just show that it's pairwise equal, right? For every two guys inside here, they got to be equal. So that means that everything's equal. Okay. So this statement just says precisely this. Okay. Now let's use the base case. The base case is easy. F of 1 is true because, well, if you have a set of only size 1, then every two elements inside the set should have the same dr number, right? Because dr is a function. Okay. Now let's do induction. Okay. Suppose that f of n is true. So what does that mean? I have a set of size n, and everything, no matter what set this is of integers, everything has the same dr number. Now take some set s of size n plus 1. So now we're trying to prove f of n plus 1. So we'll order the elements, and you can always do this for finite sets very easily. You can order it. So now we will look at two subsets of this set S. So the first subset we'll look at is the first n elements of these n plus 1 guys. And the second subset we'll look at is the last n elements. So we know that S1 has n elements in it very clearly, and Fn is true. So all elements in S1, let me make sure I don't show the error. Let me not spoil it for you. Um, uh, all of these guys have the same dr number because Fn is true, and this set is a size n. And all of these guys must have the same dr number because this guy is also of size n. So as a result, it must be the case that a1 and an plus 1 have the same dr number, and so everything has the same dr number. So f of n plus 1 is true. So I mean, hopefully you guys read the lecture ahead of time. So oh, that's a good point. I see. Okay. If you did read the lecture, you know what went wrong. But basically, what went wrong is we need to be careful about our base case. Because our inductive step is not true for every n greater or equal to 1. And why is that? Well, the problem is it's with yeah, the problem is quite simply with the one step that is strange, which is that we go from every time that this type of set has the same dr number everywhere, that implies that this type of set has the same dr number everywhere. This really doesn't make sense, right? So the problem is simply when n equals 1. And the reason that this doesn't work is because the S1 we get is just x. It's the first n things, and the S2 we get is the last n things. So there's no intersection here. So because there's no intersection, we don't have the transitive equality in between these two. So there's nothing to be said about everything in S1 and everything in S2 having the same dr number. So does it make sense why you can't use the induction step when n equals 1? Or maybe yeah, go ahead. Oh, I don't. Why not? Sorry, I guess I can't hear you for some reason. Do you mind just typing out your question? Also, does anyone else hear him? Okay, it's not just me. So I can raise my own hand for some reason. Very interesting. Yeah, you'd have to do multiple steps. So if f of 2 is true, then you can do induction, right? And just reset. So f of 2 is true, then my inductive step actually works, right? So if I had like xyz, right, then f of 2 is true. So these guys have the same dr number, and these guys have the same dr number. So these guys must also have the same dr number, right? Because we do transitive equality through y. I guess I didn't really make that too clear when I was doing the fake proof. Okay. Also, I'm curious, did anyone try looking up daikon radish? Okay. Then I get to give you a little bit of fun. Uh, daikon strategy. um, so it's completely fake. The reason I made up a completely fake math term is because some of you guys might have seen a different version of this, um, where you talk about n horses having all the same color, and you sort of line up the horses and you say, oh, the first n have the same color and the last n have the same color, blah blah blah. But it helps a little bit to see it in an abstract context. Okay, cool. I'm always very happy to present that. Um, all right. Um, oh, Sangjin added this, so I've never seen this before. Um, and yeah, we see there it's just it doesn't work there. Okay, so let's define f on an open interval mapping to R, and it should be differentiable on AB. If f attains either a maximum or a minimum value at some point inside the interval, then the derivative there should be 0. So we know that this is true, right? And you can think about it sort of intuitively, right? If we have some AB, and f is doing something, and we have a maximum or minimum inside this open interval, and it must be the case that the derivative is 0 here. Okay. This is proven by Fermat. So let's define a function. F from -2 to 2 to R, and it's just this polynomial x minus 1 squared. Okay. And we want to show that f attains a minimum at x equals 1. All right. So we take the derivative, and when we plug in x equals 1, we see the derivative is 0. So that means that there should be either a minimum or a maximum at 1. But if we compute f of 0, we get 1. Right? We plug in 0 into here, we get minus 1 squared, that's 1. And what the hell is going on here? Hang on. Sanjin, what did you mean by this? Oh, okay, so he means like minimum or maximum over the interval. Okay. So he's comparing f of 0 to be 1. What? Okay, does anyone understand this? So the bigger problem here, which I saw at the beginning, is that um, this theorem starts missing maximum or minimum at some point on the interval implies the derivative of 0. What he's doing here is he's taking the derivative to be 0 and saying that there should be a minimum or maximum here. This is where the error in the proof is. I don't really know what happened here, but basically the point is that it's actually a common error to believe that when we have a theorem that says P implies Q, to accidentally assume that Q implies P. So he's started by assuming the converse of this theorem, which is not true in general. And he has some sort of weird contradiction here that I don't really understand. Maybe I should have asked him a little bit more about this. But yeah, sorry, it's a bit sloppy. We'll just move along. And yep, we have the definition of a converse here. So if P implies Q is an implication, then its converse is defined as Q implies P. And in general, statements and their converses are not logically equivalent. because promises are really kind of one directional unless you prove them to be bidirectional. Okay. Oh, that's the end of the lecture. Okay, that was pretty fast. All right, sorry for this weird stuff at the end, but it's I think it's definitely important to be careful when you have theorems to not accidentally think about the converse. Okay, all right, that makes sense. I don't know why I just like had a stroke like reading it, but okay. All right. Yeah, go ahead.
Okay, does it work now?
Yes, it does.
Beautiful. I was wondering with the daikon radish numbers.
Yeah.
In your stage 0, it says that for any non-infinite subset of the integers, the daikon radish of all the numbers is equal.
Yeah.
Doesn't that already prove the claim without having to do any further work?
Sorry, we're just defining the statement. We're not saying it's true.
Oh, yep. Never mind.
Yeah, that's okay. No, yeah, that's stage 0 is just defining it, and then we're trying to prove it.
Okay.
Mhm. Okay. Any other questions? All right. Thank you guys for coming, and you are free to go. Bye bye.